at this point, you should feel pretty comfortable finding the surface area of prisms and cylinders. So we're going to transition into pyramids and cones. So a pyramid is a polyhedron formed by a polygonal base and triangular lateral faces that intersect, oops, that's supposed to say intersect at a vertex. So the difference here between a prism and a pyramid is that a prism has two bases that are polygons, and the lateral faces are parallelograms. So if I look at this figure here, okay, I know it's kind of hard to see because it's clear, but I've got a triangle here and a triangle here. So two bases that are triangles. And then each of these three lateral faces are parallelograms, okay? So that's what creates a prism. But when we're talking about a pyramid, we're talking about a polyhedron formed by a polygonal base and triangular lateral faces. So if I look at this pyramid, okay, again, I know it's clear, so it's kind of hard to see. I've got this base here, that's a polygon. And then I've got these faces here. My lateral faces, notice that they're triangles as opposed to right here where they are parallelograms, okay? A regular pyramid is a pyramid whose base is a regular polygon and a segment from the vertex to the center of the base is perpendicular to the base. So here I have an example of a regular pyramid, because if I take a look at this base, this is a regular hexagon because all of these sides are congruent and all of these angles are congruent. And it says a segment from the vertex to the center of the base is perpendicular. So right here, this segment is going to be perpendicular to this base, so right over here, okay? So that segment is perpendicular. A cone is a solid with a circular base, so we can't call it a polyhedron, right? Because it has that curved base, which means it does not have a polygon as a base, and a vertex not in the same plane as the base. So this would be an example of a cone, an ice cream cone. You guys know what cones are, right? So I've got a circular base here, and it joins at a vertex that's not in the same plane. A right cone has a segment that joins the vertex and the center, which is also perpendicular. So if I look at these diagrams, this regular pyramid right over here is this figure that I have in front of me, okay? The base right here is it's a regular pyramid because this base right over here has a regular polygon. It's a square. Now, notice that it also has that segment joining the vertex to the base that creates a perpendicular, that's a perpendicular relationship. That is called the slant height. And we're going to be using the slant height quite a bit. If you look at this pyramid, that's still a pyramid, okay? I still have that one polygonal base. I still have that vertex up at the top. But notice because that base is not regular, it's not a regular pyramid. It's a rectangle at the bottom, right? So it would be a rectangular pyramid. But because of that, it is going to be something called an oblique pyramid. And you can kind of see that it's at an angle where some of those triangular faces have different areas than other triangular faces. So this is oblique. Okay, whereas this one is our regular pyramid. Now, same thing with my cone. I can have a cone that's a little bit slanted, which makes it oblique. And a right cone would be whenever that height comes straight down, and my slant height is along that cone itself. Okay, now we're going to talk about finding the lateral area and the surface area of these figures. Of course, we're only going to be focusing on the regular ones. Okay, we're focusing on regular pyramids and right cones. So the lateral area for a regular pyramid is 1/2 capital PL. We already know what capital P is. Capital P is, of course, the perimeter of the base. L, on the other hand, is not something that we've talked about before. L stands for slant height. Okay, and if we go look at those definitions at the top, the slant height is different from just the height because, again, I've got this distance here, okay, that segment that is perpendicular to the base. This is the slant height. I don't want this one that comes straight down from the vertex to the ground, okay? That height does not help me find the area of this triangle. Because remember, lateral area is adding up all of these areas. And having that height doesn't help me find the area of this triangle here. To find the area of this triangle, I need the height of that triangle itself. And in relation to the pyramid, it's called the lateral height. So now you can kind of see it. So it's that lateral height right over there. Okay, same thing in this pyramid. It's that lateral height right over there. I don't want the one that comes straight from the vertex down. Okay, I want the one that's along that side. Now don't get it confused with this segment because that segment is not perpendicular to the base. I want the one that's perpendicular to the base. It creates that 90-degree angle right there. Surface area of a regular pyramid, I again want that lateral area, so I still want that 1/2 PL. But I have to add on, this time, one base. Instead of two bases, I'm going to add on one base. So that's going to be plus capital B, which again represents the area of the base. Okay. All right, let's do a couple of examples. So it's saying finding lateral area and surface area of pyramids. So I'm going to start off with lateral area. The formula is 1/2 PL. So if I look at my diagram, I want to first find the perimeter of the base. Well, if that's 6, that means that's 6, and that's also 6. Remember, we're only dealing with regular pyramids. So that base is going to have all 4 sides congruent. So 4 times 6, of course, is 24. So I have 1/2 24. And now I want the slant height, which luckily they give that to us. The slant height is this segment right over here. Okay, because again, it's perpendicular to that base. And so that is 15. And then all I have to do is simplify that, which leaves me with 12 times 15, which is 180 feet squared. Now to find the surface area, I'm going to again just take that lateral area, which is 1/2 PL. I'm going to add on the area of my base. So to find the area of my base, again, it's a square. I'm just going to do base times height. 6 times 6 is 36. So I already had my lateral area, which was 180, and now I'm going to add on 36 to that. So my surface area is 216 feet squared. That's all there is to that one. Now, if you look at the next example, this one obviously is going to be a little bit more complex because that base isn't a square, right? It's not a triangle. It's not something that we use all the time. It's actually a hexagon because it's got those 6 sides. So we're going to have to put in a little bit more work to find the area of that base. But just like before, let's start by finding the lateral area, which is 1/2 PL, where L again stands for the slant height. So I have 1/2. My perimeter of my base. Now the nice thing about these being regular polygons is if you have one side, you've got them all. So my perimeter is going to be, this is 1, 2, 3, 4, 5, 6. This is a hexagon. So 6 times 10, which is 60. And again, they were very kind and they gave us the slant height, which I can see because it's perpendicular to the base right there. So that means it's 16. Half of 60 is 30. 30 times 16 is going to end up being 480 inches squared. To find my surface area, I'm going to take my lateral area. I'm going to add on the area of the base. And this is the area of the base is what's going to take me a little bit longer to find. So let's first go ahead and say, okay, well, I know that my lateral area was 480 plus Now to find the area of the base. Now, if you use hexagons a lot, you need to start getting used to specifically hexagons because they show up so much and they have a lot of really cool features that you can use over and over again. But if you're not used to that, I'm going to go ahead and show you one more time about how you approach that. So I do like a little section of my hexagon. Remember the formula for the area of a regular polygon, specifically for a regular polygon that we can apply to a hexagon is 1/2 AP. I've already found P, okay? That was 60. We found it earlier. I have to go find the A, which is this piece right over here, okay? Now, because I know that this segment is 10, the apothem bisects that side, which makes this 5 and this 5. I need to now go find that radius, and I don't need to find the radius. I'm going to use the radius to create a right triangle, okay? And that right triangle actually ends up being a 30, 60, 90 triangle because if I extend this out, this is 360 divided by 6, which is 60 degrees. These angles are bisected. 180 minus 60 is 120. 120 divided by 2 is 60 degrees each. So that makes this a 30, 60, 90 triangle where 5 is the short leg. So I've got 1, square roots of 3, 2. Don't care about the 2. That's not going to help me find my apothem. Over 5. So A is equal to 5 square roots of 3. Which means this right here is 1/2 5 square roots of 3 times 60. So that's 30. 1/2 of 60 is 30. 30 times 5 is 150, which is 150 square roots of 3. Okay, now I got to ask myself, can I add those together? Can I combine them? They are not like terms. Not if I want to keep them in exact form, so I'm going to leave it just like that. So my final answer is going to be surface area equals 480 plus 150 square roots of 3 inches squared. Okay, all right, now let's talk about cones. So the lateral area of a right cone, the formula for that is going to be pi RL. And the surface area for a right cone is going to be, again, that lateral area, pi RL, plus my base, which is a circle, so pi R squared. Finding lateral area and surface area of right cone, so we're going to do this cone right over here. But notice this time we were not given the slant height, which I need to use my formula. However, you might recognize that, hey, I see a right triangle right over here, okay? You can use that right triangle to find your to find your slant height. So I've got LA equals pi RL. So pi, my radius is 8. And now I've got to go find my L. Now, if you remember your Pythagorean triples, you'll be able to get your L, boom, just like that. But if you don't remember, you're actually going to have to go do Pythagorean theorem. 8 squared plus 15 squared equals L squared, which is 64 plus 225. So 289 equals L squared. Take the square root of both sides. So my slant height is 17. Let me put it in a different color so we can differentiate. So that right there is 17. It does not tell me to round or anything like that, so I have to keep it in terms of pi. So my lateral area is going to be 136 pi inches squared. Now to find the surface area, I just have to add on that circle, pi r squared. I already have 136 pi plus pi times my radius, which is 8 squared. So 136 pi plus 64 pi is a nice around 200 pi inches squared. And that's all there is, okay? The only thing you have to keep in mind is the difference between the height and the slant height. Don't accidentally use the height when you're supposed to be using the slant height, okay? And next time we're going to be talking about composite figures involving cones and pyramids.